Falling with style. That describes bats because they are among the best flyers the world has ever seen, even better than us and our machines. And today in our podcast, we're talking about why this is the case. In fact, everything about how a bat flies is pretty remarkable. For example, did you know that out of all living flying animals, bats have the highest wing weight to body ratio? In other words, relatively speaking, their wings weigh more than any other animal on the planet. This is due to having many bones and relatively large muscles. And some researchers suggest that because they have such big wings, so heavy wings, they should be far less efficient at flying and not really good at flying compared to other animals, but it's actually the opposite. And in this paper, we actually be looking at why this isn't the case, why they actually are very good flyers. And in this paper, Falling with Style, bats perform complex aerial maneuvers, aerial rotation, by adjusting wing inertia. These researchers describe why bats are so good at flying, especially considering conventional science which suggests otherwise. They also go into how other flyers, like a fruit fly, can't do many of the flying maneuvers that bats can do, even though they are much lighter and their wing to weight ratio is much lower. And these researchers looked into a 52 degrees of freedom model to analyze how bats can fly so well. 52 degrees of freedom. That's a lot of freedom. They probably don't even pay taxes either, these bats. Anyway, I noticed that if you take the A out of the word bats, it becomes BTS, which is everyone's favorite band. Anyway, let's move on. In fact, even for bats just to land in their position of choice, upside down, they have to flip their bodies up from flying position to their resting position. That's like if we wanted to go to bed, we'd have to do some kind of gymnastic routine before we can even lie down. That's what bats have to do every time they want to hang on to something. So to investigate bats' flying abilities, these researchers tested two species, the Seba short-tailed bats, which Latin homies refer to as Carolia perspicillata, and the second type of bat is called the lesser dog-faced fruit bat, which I guess is in contrast to the greater dog-faced fruit bat. This bat is also known as Cynopterus brachiotis in Latin. So they train these bats to land in a square, which is surrounded by three high-speed cameras as shown in figure 1. So this bat here would be flying around and they were encompassed by these three high-speed cameras. And the cameras had a frame rate of 1000 frames per second. Even with that frame rate, they only were able to capture between 500 and 1500 frames per maneuver of these bats. That's how fast these bats twist around as they're trying to land. So they managed to train these bats by covering everything else in smooth plastic sheets. So I guess this was the only place that the bats could hang from, this small square bit that wasn't covered. So actually this is quite funny because when I was doing my PhD, I remember leaving the uni around dusk several times, and I would walk over this bridge at the back of my university. And I would often see these huge bats, like 3 feet in width, flying around. And these bats are called flying foxes. And I was just stunned at how huge these things were. And actually, when I was preparing for this podcast, I looked these ones up on Wikipedia. And Wikipedia says that they don't actually exist in my city, apparently. So apparently what I was seeing was just an illusion, according to Wikipedia. I guess it's possible. I did work pretty long days back then. Anyway, these flying fox bats, even though they're like 1 meter in width, they only weigh like 2 kilograms. So that's because their bones are so light and their wings are pretty much just skin. Anyway, these researchers used their high-speed footage to recreate the bat and their wing and body kinematics during their flight and tumbling around. From this relatively simple method, they found 23 joint angles describing each pose of the bat's wings. 23. So to give you an idea, for our arms, I guess we only have 3, really, the shoulder, elbow, and wrist. These bats have 23 per arm. So the 52 degrees of freedom that I mentioned earlier comes from 23 for each wing and then 6 for the body, making 52 in total that these bats can rotate about. That's pretty complicated. So in addition to the aerodynamics, the researchers also measured the distribution of the bat's wings and bodies to see how the inertia was used in their flight. The reason why they did this is because they believed that a bat's inertia could be used and that these to fly and to orient themselves and reorient themselves, and that these bats did use it to help them rotate during these maneuvers. So figure 2 shows the bats flying, trying to land, failing to land, and then flying off again. So this bat comes in, it's flying around normally and then flips upside down, tries to grab the roof. There's nothing to grab, so it's a failed landing attempt and has to obviously fly off. So it has to reorient itself to a flying position and then flying again. So for this landing maneuver, we actually have on the top the like high-speed cameras, and then on the bottom row is the like computer enhanced images of these with the different points in these bats' wings denoted by these nodes, these red nodes that can rotate around. So for this landing maneuver, the bat initially flapped both of its wings symmetrically, as you can see in like the first figure here. Then it starts to twist, and it twists about all three orthogonal axes, so the X, Y, and Z axes. It then like flips itself upside down, so its feet are above its head, and then comes to rest. But if the bat fails, so in figure 3, we see that the bat fails, and then it comes off, flips back around, and flies off. These researchers say that it is during the flipping upside down phase, the initial one, so from 1, 2 to 3, where the bats flap their wings asymmetrically. So interestingly, it retracts one wing during the downstroke while keeping the other wing extended. This obviously creates an imbalance in lift being produced and creates a roll as well as a yawing change. So that means that the force produced, it's not only in the rolling direction but also the yawing, and or there's an inertial coupling between the rolling and yawing moments. So what's more interesting is that these researchers say that the right wing is more extended than the left wing. So I guess that means that the right wing is always more extended. I wonder if all bats do it the same way, or if there are left-handed bats and maybe right-handed bats. In figure 3, you can see that the asymmetry in the wings extension. So let's go to figure 3 here. We have some graphs showing the angle of these wings and the wing extension through the flapping. So in the third subplot is what we're looking at here, and the third dashed line, so here, all of a sudden the left wing gets tucked in while the right wing slowly retracts. Let me zoom in a little bit so we can see this a bit better. We have the wing extension from, I guess, 0 to 100% in the y-axis, and from the third dashed line, they're fairly symmetrical in terms of the extension, and then all of a sudden it pulls in its left wing, so it's almost completely near its body. It's only extended 25% of the entire way, whereas the right wing is extended over 75%. And then at the fourth dashed line, so this fourth one here, is when the bat has to recover from a failed landing attempt, and both wings pop out symmetrically again, so it goes from asymmetric back to symmetric when it tries to fly off again. So I wonder if over time, because it's pulling in just one wing, I guess the same wing every time as far as I can see, if over time one wing becomes a little different to the other, and I mean if you continuously do the same action with one side and not the other, I'm guessing that changes to the muscle and even the joint would occur, where one would get bigger, maybe the joint would become more flexible, I don't really know, but it would result in some sort of asymmetry in the body of the animal. So moving on, in table 1, they actually compare bats with fruit flies. So let's go to table 1 because there are some pretty cool numbers here that show just how different a bat is to a fruit fly. And fruit flies are somewhat similar to a lot of flying animals, particularly flying insects. So one interesting thing is that both bats and fruit flies have the same drag coefficient of 2, which is really high. I mean, that's like higher than some objects traveling at transonic speeds. But that is also because they're flapping, which means that they're producing lift, and the way that most animals flap, they are somewhat inefficient in terms of their lift drag ratio, but they can produce a lot more lift compared to how much they weigh. So that's the trade-off there. In that respect, they are much better flyers than our machines, but still the drag coefficient of 2 is quite high, which is why so many flying animals need to eat so much. For example, apparently pigeons, they need to eat half their body weight per day just to survive because of how much energy flying takes. And that's against the average pigeon. There might be some thinner pigeons or some like fitter pigeons that might need less food, I don't know. But half their body weight, that's how inefficient, that's how much energy they need to produce their type of lift. But then they can carry a lot more than our machines. But anyway, another thing that stands out is that bats have a much greater relative moment of inertia compared to fruit flies. So this third row here, the ratio of wing to body moment of inertia for the bat is 5 compared to the fruit fly, which is 0.02. That's 250 times greater for the bat than the fruit fly. And the reason why this value is so important is not just the overall moment of inertia that they also give, is But because these animals are so different in size, this ratio sort of normalizes these values so we can compare them better. So the bat's one is literally 250 times greater than the fruit fly with its wings compared to its body. That's how much heavier their wings are, and because of these wings further out from the mass, that increases their moment of inertia, and the greater the moment of inertia is, the more newton meters you need to be able to rotate this thing around by the same amount at the same angular velocity and angular acceleration. So it would actually be weird if the bat had an overall lower moment of inertia than the fruit fly, simply because of how big it is, but this ratio gives us a better idea as to comparing the two. But the fact that it has a much greater relative moment of inertia is interesting because it means that it is much harder for this bat to turn, and this bat is actually turning quite often when it tries to land. Now, this is something that the authors initially pointed out as being detrimental to the bat's aerodynamics and acrobatics. They argued that having such a higher moment of inertia means that trying to turn is much harder. But on the flip side, it also means that once you start to turn, it is much harder to stop turning, which means that if you fling yourself, you will tend to go in that direction even more. So it really has to do with the starting conditions, whereas for something with a much lower moment of inertia, like a fruit fly, in order to rotate a lot, it has to constantly provide relatively high moments through the rotation, because even if you have a small disturbance, because its moment of inertia is so low, that has a greater effect on it stopping its rotation or rotating it differently than what it should be doing. So the bat's having a high moment of inertia kind of means that it can follow its path a bit better with its inertia. So to look into this idea in general, these researchers then used their 52 degree of freedom model. And in figure 6, they show how their model compares to the experiments. So let's go down to that figure here. Here we go, let's zoom in a bit. So we have the roll, yaw, and pitch moments, and the dashed line is the mathematical equation, so that mathematical model. The solid line is the experimental data that they got from their high-speed cameras. Their model is quite good. It gives very good, very much the right trends between the roll, pitch, and yaw, and even for the magnitudes for most of the maneuver, it predicts it very closely, if not identically, to the experimental data. So it's a very good model, it looks like. And from this model, they confirmed that for the reorientation part actually, of the maneuver, not just orientation, but reorientation because it's failed to land. So for the reorientation part of the maneuver, so when the bat tries to land, fail, and then has to recover during the recovery phase, it is the inertia of the wings, so they fling them around the right way, that makes the reorientation work. They say that it's not really aerodynamic forces that help the bat reorient, simply because the inertia is just so high. That's what they sort of conclude from this thing, and also considering that one wing was much smaller than the other. It was pulled in more. Now, this is a surprising result. Is this a surprising result? In my opinion, not really. The reason is because if you look back at figure 2, let's go up to figure 2 here. So in figure 2, we see pictures of the bat do this exact maneuver of where it tries to land, fail, and then recover into the flying position. Subfigures 4 and 5 show this recovery part. Now, during this process, there are only 3 possible forces, really. One comes from aerodynamics, so that is from the wing flapping and even its body catching the air, and then manipulating that to change its body position. The second way is from inertia, which causes the corrective moment. And the third is potential force, potentially from the bat pushing off the wall. Those are the 3 potential ways that the bat is reorienting itself. Is it the aerodynamics, the inertia, or maybe it gives the wall a little love tap and goes back the other way? The authors say from their findings that it was mainly just the inertia of the wings, where they fling their wings out in a certain way, and that reorients them in the right direction. Now, from these pictures, the bat doesn't seem to push off the wall, from what I can tell. So we really only have 2 possibilities for the bat to reorient itself, from the aerodynamics or from the inertia. For the aerodynamics, because the bat is flying so slowly, it's trying to land, so its speed is very low, obviously, and that means that there's minimal aerodynamic force that the bodies can generate, and so that also leaves only the wings that could generate appreciable lift. for the wings from these figures, I don't see too much flapping. In fact, I only see one upstroke and the wings seem to move about the same amount. So there is not much asymmetry here in this figure 4 here. If you go from figure 3 to figure 4, both these wings kind of flap out by the same amount and up. So perhaps the only asymmetry might be that the left wing is a little less extended than the right wing here compared to here. But not that much. And in fact, in reality, if you wanted to create the largest moment possible through aerodynamics, you would flap one wing down while flapping the other wing up. In this case, both wings flapped up. So as such, I don't expect much of a moment to be created aerodynamically, and it doesn't make much sense to me that the bat is trying to produce a moment through aerodynamics here. So that agrees quite well with the researchers. The only way that a moment could really be created if the wings rotate about different axes, so the forces generated don't cancel out and produce zero moment. But from these subfigures, it doesn't seem like that. So it seems like there's not much of a moment created by the aerodynamics. So by that, the only way left that an appreciable moment could be produced is through inertia. So after seeing this figure, it's not that surprising to me that the bat isn't using aerodynamics much to produce the corrective moment. And I mean that the bat isn't primarily using aerodynamics. I imagine that there is some small contribution, but it seems logical from these pictures that the bat primarily uses inertia. And the data collected by these researchers prove this. The authors provide one reason why bats rely on inertia and not aerodynamics for this corrective maneuver. They say that because the speed is so low, that the amount of aerodynamic force they can produce is low. And that is definitely true, but they can still produce some amount of force. So in my opinion, is that it may not be just because they won't produce a huge amount of force, so they don't use their wings, but because if they could produce even more force, that is beneficial. So why would you produce only a little bit of corrective force by throwing your body around when you could produce even more with throwing your body around and flapping your wings? So my idea is that bats don't try to correct themselves through flapping, through aerodynamics, because it may be dangerous to their wings. So if they are trying to grab onto something, then chances are that there are other things around them, and they're kind of in a cramped space. There might be some twigs around, or other bats, or an overhanging rock, etc. So if they try to flap, which requires their wings to be completely outstretched, at least if they want to produce as much force as possible, they risk injuring themselves and possibly even other bats, because they like fling their wings out. They might hit a wall, or they might hit another bat or something. So I think one major reason why they don't rely on flapping to reorient themselves is to reduce the risk of injury and reduce the risk of starting a ruckus with other bats by hitting them. So that is my opinion, and I'd be interested to know what your opinion is about this idea as to why they don't use aerodynamics. So let me know in the comments why you think bats rely primarily on their inertia to correct their orientation instead of flapping their wings. And with that, my analysis, we come to the end of our podcast. I liked it because I like talking about the aerodynamics of flying animals, especially ones that fly differently like bats, and things that kind of kick the system, like, physics is saying, well, because you have such a high moment of inertia, you shouldn't be able to rotate this much, but bats go, I don't care, I'm still going to do it, and then they do it. So that's pretty cool. So if you like this podcast as well, please like it. And if you want to see more like this, hit the subscribe button or follow the follow button, whichever platform you're on. And big news, we just released our intermediate CFD course. It covers how to do CFD well, including how to do a high quality grid convergence study or grid independent study, whichever you want to call it, same thing. How to generate a high quality mesh, the differences between RANs, DES, LES, and DNS, and when to use each one. We also go through turbulence models, explaining each one in detail, the strengths and weaknesses of each one, and when to use each one. We also go through how to properly validate your CFD, which is actually an art in itself. Like it's not as easy as you think it is, and we go through some of the reasons why and how to actually use that to improve your mesh. So if you do like your CFD and you try to validate it and it doesn't come out right, you can actually use that data to figure out where to improve your mesh or things like that, and use that feedback. So we go through that as well. We also cover transient simulations and how to pick the right time step, as well as how to do rotating geometries. So it's a really thorough course, and if you want to learn how to do these things and give yourself a leg up with new employers, take that course and you get a certificate as well at the end to prove it. And you can find that course and link in the description. And with that, we come to the end of our podcast. So I'll see you next one.